Okay, so today we're gonna see strings. Pretty much we all know what string is. And we will try to cover some good technique and also to see some interesting algorithms related with strings. So in computer science we say string is like a sequence of characters. We define it as that, and it could be a literal constant or a variable. Some languages implement string as a mutable, and there are also like we'll come to that. And there are also like it could also be a constant, which we pretty much get used to. And we can say like strings are everywhere, starting from forms representing data. And even one application I found is even for communication in embedded systems, we use strings because when we use Bluetooth, we only have like 14.4 bytes per second, and it usually means sending one character, and to terminate a connection, we could send like another character, and they use this technique even for communication. So we can say like one of the most useful data structure in computer science is a string. And when we see the implementation, there are languages which allow mutable strings like Swift and Ruby, and also when it comes to Java, Python, and C-based languages, not all of C-based languages, but Java and Python, for example, they use an immutable. So once it is created, it acts as literal constant. You can't modify it. And also like Prolong and some other languages, like they don't actually implement strings. They consider it as an array, and people are expected to work with that, to consider it, to manipulate it as a string. And one other thing about string is like their encoding type, because we see strings as just a word or a sentence, but in computer there is a different way of representation, and this have been like since 1950s. Even for, I think for Enigma communication and other things, they use a different kind of encoding scheme. And one of the most common one when it comes to computers is the ASCII coding, which uses 7 bits, and it have like 128 different possibilities. And the problem with this one is at that time we only use English alphabets and numbers to represent string, but when we introduce new languages like the Chinese characters and the Amharic and also different Roman characters, it wasn't enough. So they started working on different implementation like the UTF-8, 16 or 32, and those are related with their bit number. Since this one only have 7, the UTF has 8 bits, so it represents more wider ranges and more characters. But there is a problem with this also, because it could run out. It could run out of possible representation. So now we normally use the Unicode one. The Unicode is kind of more complicated than just representing it as a sequence of characters. For example, we see like if A is 65, then B will be 66. But internally the Unicode works in a different way. There is a different way of deciding whether there should be a character within or not. And there is a different technique for that. And also, if we decide there should be a character, or if we decide we should add a character into the representation, and what should be that number. And for example, we could give like similar values to A series, and we're only gonna change 1 bit to represent the next form of A. So, and that is also the second technique they use. And the third and the final one is how could we map it from Unicode to any system, because Unicode come in a very later stage of computer science. So there are still legacy systems which uses UTF-8 and even ASCII for communication. So there need to be conversion between them, and we should also, for programmatic reasons, we should also keep the sequenceness of like characters. It should be kind of continuity. It should have a continuity, and for that, it also have another form of format exchange, and they work. These three things work in pipeline to give us what we see as string as to do, like to represent it and to use it. So this is just a high level overview, and yeah, okay, we thought that was the representation. And one other thing about the string is how do we represent them in our programs? Like, how do we know string is what is the start of string or the end of string? So in a C-based language, we use the non-terminating string type. The non-terminating being like this one. When a string ends, always a string ends with slash and zero. Okay. So in C-based languages, a string ends with a slash and zero. This will represent that this is an end of a string, and also there are a different way of representing the end of a string. We get used to this because almost pretty much all languages nowadays use this form of representation. And also there is a byte and bit terminated ones. This one, for the byte one, they use different special characters. For example, assemblers use $sign, and also I think mainframe and CDC computers use colon, and also there are the old IBM computers, they use kind of quotation or something like that. But nowadays, since we normally use these characters in our strings, it would be better to use this null character to terminate it. But there is one downside to it, maybe you could guess. Like in a computer security perspective, what would be the problem with non-terminating strings? Okay.
If I manually enter this as a string, as part of my string, the computer might misinterpret it as the end of the string.
Yes, but that wouldn't be a very severe problem. Like, you are close, but maybe another person.
What was the question?
What would be like the downside of representing strings with non-terminating characters? What if we don't provide this value when we create a string? What would happen? Now we have a check for it in our compilers, but in early days, this would cause buffer overflow. So an attacker could write a code and could append it to a string, so that when it is read, this machine codes would be loaded into our RAM. So they would have they would get remote level code execution, and that was very problematic. But now we have appropriate checks to combat that. And the last one will be the links prefixed or Pascal. I think this is only used by Pascal, so we usually call it Pascal string. So what they do is, first they represent the number of the characters before the start of string, and then the string continues together. So these are different representation of string. And okay. So one other thing, like one of the most very common application of string will be string pattern matching or stringology, and pattern matching is just we'll have a string and we will have another pattern. We'll try to find the existence of this pattern inside the string or inside the text. So it is still an active part of computer science research. There is still a lot of development in it, and there are also very common and well-known algorithms. Usually these algorithms in our language, like in Python.find, it uses the Boyer-Small algorithm to discover patterns, and its applications range from almost everywhere, starting from bioinformatics, genetics, to even intrusion detection systems and search engines. It has a lot of applications. So the first one is the Knuth-Morris-Pratt algorithm, or what we call KMP. KMP is a bit advanced, and honestly, I don't think you would be expected to fully implement it in an interview setting. But knowing it is a huge plus for you. So I would talk about it in a high-level manner. So let's say we have a text. So in KMP, what we do is when we are given a pattern, we first kind of try to find what is the maximum prefix and a suffix within the pattern. For example, when we consider A, just A is the maximum prefix and the suffix of the string up to this point, right? And when we include up to B, these two don't match. These two don't match, so the maximum prefix, which is also a suffix, will be 0. So when it comes to C, this is also the case. Also up to D. And what would happen when it comes to A? So we have A on both sides, right? So we have one character, so the maximum prefix, which is also a suffix, is A. And
Mohammed, just to be clear, can you remind us what were the definitions of prefix and suffix?
Okay. Prefix is the words which starts from the zeroth index up to some points, some arbitrary points. We will pick that. And here we are trying to find the maximum, so we go as much as we can until we cannot go any further.
Like here the prefixes are A, AB, ABC, ABCD, ABCA.
Yes.
And two more, right?
Yeah.
And how about
And the
suffix?
suffix is, for example, if we consider strings up to only this point, it would be like doing the prefix process backward. So we'd say like A, AD, ADC, ADB, things like that. So
But this time from end point we are coming back, right?
yes, exactly. So here we have A both sides, so the maximum prefix, which is also a suffix, will be 1, right? So what would happen when we add B? 2, so it will be 2. Yeah. So and C, it will be 3. So what KMP does is, when we found a match, for example, let's say we found a match up to this point, when we compare, so we have a match, so we don't need to go back and start again when we have a kind of a prefix. For example, going back wouldn't matter because they don't obviously match. So the next thing we could do is, like, we could try to find a way to move this string back so that we would use that to our advantage. For example, when we match up to this point, the only mismatches happens here. So rather than trying to go backward and start again from the second character, what it does is it will move the string and start up to this point. And we know when we do match, we can go again and just push it. So like we try to take the advantage of knowing our backward matches in order to not do repetitive matches, so that like for example, when we consider this one and this one, if this match and if this doesn't match, the next one doesn't match, we could just say like this one would match and we'll try to compare the next one. Do you get the point? No? Okay. Okay. So let's say we have a mismatch here. So what we could do is first in a naive approach, we could go back and we will start to match from the second element and starting again. And we already know that these two matches. So what we could do is we try to find what is the maximum, what is the last matched variable. So what is the last prefix, which is also a suffix, which would be in this case, we will come here. So the last prefix, which is also a suffix at this point, is 0 because we don't have any d as a start. So there is no point in going back and trying to match again. So we could just escape and start from it. And we can continue this, we can continue doing this so that we will kind of know not to do repetitive match. Do you guys get the idea? The high level idea. Okay. So I think I'll send you a video on this if you want to explore it more, but I don't think you will be expected to fully implement it in an interview setting. Just mentioning it and saying that I would use this technique to make my search more efficient would be much better. So yeah, I think so. And the other one, and the very common one, would be the Boyer-Moore, and it uses some similar techniques. It's called the bad character and the good character heuristic. And if you guys also want to know more about that, I'll send you another video. And the last one would be the Karp-Rabin. This uses a kind of a hashing. For example, to match a character, these two characters, it will hash this value and this value as a start, maybe the entire value, and it will try to match their hash value. And if it didn't becomes equal, what it does is it will move one character and try to calculate another hash, and it will try to match. For example, we have like 1, 2, 3, 4, 5, 6, 7. So 1, 2, 3, 4, 5, 6, 7. So the hash value of this, let's say it is 1878, and the hash value of this, let's say 65. So 78 and 65 are not equal. So what it tries to do is it will remove A, and it will add one character, and it will calculate the hash value of this, and it will try to compare. And when it is equal, it will do a character by character comparison, and it will say I found the match. So one question would be what would be the cost of calculating the hash value? In this algorithm, it suggests we can calculate the hash value in constant time after we get the first hash value. For example, for the first one, it will take of n time, n being the number of the pattern. Then after that, we can calculate the next hash value by just using the previous one and adding one character on top of it. So it's kind of complicated, but yeah, maybe you guys can explore it if you want to see it more. And yeah, I think that's enough on pattern matching. And finally, for Python users, I think Python is considered very good for string processing. Actually, R is considered very good for string processing, but many people prefer Python because Python is currently kind of a de facto standard for machine learning. Like, we normally use Python very frequently than we used to do before, and also it has a lot of string manipulation library. Maybe it's not as good as R, but it has a lot. and it also have like a very big community support. But one good thing about Python when it's compared with R is it's usually much faster. So nowadays we use Python more frequently for string processing. So now let's try to see some maybe common methods about on Python string processing, and we use these methods, and there are some other on the next slide very frequently. The first one would be the split one, and we all know what the split function in Python does, right? You guys are aware of it? Okay. So the internal implementation is written in C, so it would be hard to describe it, but it has a time complexity of n, and it will work whether we separate a separator or not. If we don't separate, it will split the string using a space. So yeah, I think the next one would be strip. What strip does is it will try to remove a character from the start and from the end of a string. So it will have kind of 2 pointers, and it will push the 2 pointers until there is no that character doesn't exist anymore, and it will kind of cut it and return it. So you get the idea, right? So this will also take n time, and so the join operator, it works in n time, even if we give it like a lot of string. Being n, I mean when we have a string of like of1 and 2 and 3, it would be the addition of this 3, because since it knows how much memory it would cost, it will try to allocate it inside a RAM, and it will just kind of do a character copy before creating string and returning it. So this is one of the most like efficient way of concatenating a string. And the find uses the Boris-Moore and Horspool algorithm in order to find the patterns, and also the count one, and also the count operation. And when we use, have you guys used addition for string concatenation, by the way? Okay. Why do you prefer it, maybe? As a simplicity or just simplicity? Okay. So when we use addition, what will happen is, like, actually there should be a multiplication. So what it does is actually it will try to create a new string each time we concatenate 2 strings. Like it has a string for the first one. Since strings are immutable, we cannot append it on top of it. So it will create another string on top of it. So this is usually the least efficient way of concatenating string. And you should definitely use the join operator. So, okay.
I have a question. So the join was, what was it, something join plus?
The join, it will try to allocate the memory enough to hold the entire string, and it will append it. So, for example, when you have 2 strings, it would work the same as the addition operator. But when we have a lot of strings, each time it will create this string, it will save it. Then when we use the addition on top of it, and it will add this string and it will create another one. It wouldn't be a kind of a copy, it would be like create a new string and just delete it and add another string and create a new one. So yeah, that is the difference between the two.
So the time complexity gets higher for the...
Yeah, it would go up to n squared using the amount of strings. So, do you guys have any question? Do you guys get the idea of the slides before this in general? Okay, shall we go to the questions? Okay, the first one will be to reverse a string. Okay, how do you reverse a string? Like, is there anyone who wants to show it? Just the CDO code will be enough. Yeah, you don't need to write the entire CDO. You can write it. Let's do it.
Assuming S is my string.
Okay, what will be the time instance for this?
All time.
For the time? For both.
M space. Well, I'm copying this and I'm assigning it to S. Yeah, basically. All time.
Okay. Yeah. Any different way?
Does this use extra variable or not?
It's a what?
This uses
Extra, it doesn't use extra variable.
Yeah.
It does. No, it doesn't. It doesn't.
Okay. No suggestion? Yeah, I think in Python, since strings are immutable, we need to use extra memory in order to create one. Also reverse it. And I think we can go to the next question. So on the answer, we could use a list, and we can iterate over the string, save it in reverse order, and use the join operator to efficiently concatenate it. Okay. The next one would be checking if two strings are anagram of each other. So anagram being one string is created using all the characters on the another string, but maybe the order is different. And how do we check if these two strings are anagram of each other? So you guys can work on a paper.
First, we'll make a map from each character to its count. For example, for the word anagram, we make a map from each character to its count. For example, there is 3S, and there is 1N, 1G, 1R, and 1A, right? For the next string, we don't add the counts, but we will subtract the counts. So the next string is anagram or whatever it is. For n, in the map, if there is n, I will decrease the count, so the count becomes 0. For a, they exist if the character doesn't exist, so I will break the loop and I will return it's there not anagram. So this way I will eventually it becomes 0. G for G it will also be 0. And for A, for R, they all become 0. Then the last check is if all the characters are 0. If all the counts are 0, it means they are anagram. That's one way of doing it. But I think there is also another. That's all.
Do we need the last check?
I mean, we need to check if all the counts are 0, right?
Can't we make sure just
By
just accessing it and when we are accessing this, we are also doing a check, right?
yeah.
So do we need the final check, or how can we avoid it? Like, what would be the edge case that requires us to do the final check? What would be the edge? Okay. For example, let's say we don't have M here.
Then M
What
would be
we have.
1, right?
M would be 1, right? Yeah. So, you guys, you get the idea, right? So, how do not?
Yeah. I think it's because it's an ON time. I'll just take the last ON check.
When you check?
But I think now.
Okay, I think the problem is if we have like less characters here, there might be values which are not being decremented. But in order to avoid that last check to go over through the dictionary again, you can just check the links of the two strings as a start, and if the links are equal, you can always guarantee that they could be anagram if we still have a value and none of them are like negative or below 0. Yeah, I think this would have a time complexity of or in time or space. Both?
Yeah, both.
Okay, both. Anyone with different idea? Maybe? Okay, so on.
The idea is same, but instead of using hashtag, we can use counting array.
Counting.
Maybe little.
It will be missing. So it would have a space of,
Space complete. Yeah, actually it doesn't change anything.
but it will, you can say like it will be constant, but